Can everyone see my title screen?
Yep, looks good.
Yes.
Okay, so, yep, talking about, as this says, math coprocessors before the x86. So I apologize that one, this is only peripherally related to calculators. You'll see the calculator connection partway through this. Two is that I do not have any pretty photographs or diagrams or anything like that. So this is just going to be text with a lot of bullet points. And with that said, I guess we're ready to go here. So almost everybody has PCs or Macs or whatever now, and most of them have x86 processors in them, except the latest Macs use ARMs. And everybody's accustomed to, in general purpose computers, whether they be Mac or PC or whatever, that they don't even have to think about floating point. That's arithmetic. That's now built into the processor. You don't have to buy a floating point coprocessor anymore like you did 20 years ago. But before the x86 and the 8087 floating point coprocessor that came with that, there were various other math coprocessors, and so I'm going to talk about those. I'm going to give an introduction to the basics of floating point arithmetic first. This is probably old hat to everybody here, so sorry if this is at too elementary a level. Then I'm going to preface the coprocessor part with what floating point hardware existed in computers before the microprocessor revolution, and then I will actually describe the early floating point math coprocessors. So floating point provides a way to approximate real numbers. There is no way in a computer to represent the vast majority of real numbers, but we can provide approximations spanning. Part of the motivation of floating point numbers, as compared to, say, integers or rational numbers, is that we want to be able to represent numbers in a very wide range. So typically floating point allows 75 or more orders of magnitude of range in your numeric representation. Only a limited precision. Now there exist, as Cyril mentioned earlier, there exist arbitrary precision math packages, but your normal floating point arithmetic representation usually has less than 20 decimal digits of precision, sometimes a lot less. Single precision is only around 6 digits. And again, unlike the arbitrary precision arithmetic libraries, normally floating point numbers are represented using a small number of bits in memory, so often 32 or 64 bits, which would be 4 or 8 bytes, respectively. So the most common floating point formats used are either binary floating point, which is radix 2, or decimal floating point, which is radix 10. And computers mostly use radix 2, and that is because the hardware is simpler and faster. Calculators mostly use radix 10, as all of us who've used HP or even TI or pretty much any brand of calculators know. So in either radix, whether it's binary or decimal, there are common fractions that cannot be precisely represented. For instance, 1/3, as everybody knows, in decimal is going to be 0.333, etc., repeating, and so there's no exact representation in decimal. And the same is true for 1/3 in binary, and that is because 3, the denominator, is relatively prime to the base of 2 or 10. If we had, hypothetically speaking, a base 3 floating point number, then we could represent 0.3 exactly. So in particular, calculators use radix 10 because humans generally use base 10 for number representation, and we would like to be able to represent negative powers of 10, like multiples of 0.1 or 0.01 or etc. We'd like to be able to represent those exactly. From a numeric analysis point of view, it doesn't matter whether so much whether those are exact or not. But if you punch in 1 divided by 10 on your calculator, you really probably want to see 0.1 and not some other approximation of that, like 0.099999. So a floating point number consists of 3 parts. There's the sign of the value, because we might want to represent a positive or a negative number. There's the significand, and most people are not familiar with that term, and it's often referred to as a mantissa, and that is incorrect. That the word mantissa has a very specific mathematical meaning that has almost nothing to do with floating point arithmetic. So the correct term is significand. The significand is the significant digits of the number. And in a floating point number, the bounds of the significand are very specific. It's essentially a floating point number. The significand always has exactly one digit left of the decimal point, or the radix point, I should say, since it could be binary, and that digit can't be 0. Then there's the exponent, and the exponent is an integer value that represents a positive or negative power of the radix. So base 10, your exponent. Well, for taking the HP calculators as an example, the traditional ones allowed an exponent range of minus 99 to plus 99. More recent ones, some of them are minus 499 to plus 499. So the absolute value of the floating point number, which means I'm not considering the sign, which was separate, is the significand times the radix to the exponent power. So if my number is, for instance, 6.02 times 10 to the 23rd, which is Avogadro's constant in decimal floating point, then the 6.02 is the significand, and the 23, the 10 to the 23rd, 23 is our exponent. In floating point representations, 0 normally has to have a special representation because, as I said previously, the significand can't actually be 0. So there'll be some other value in memory that is used to represent 0. So a little bit of snarky comments here. While floating point numbers are supposed to represent real numbers, an IEEE single precision float can represent 0% of the real numbers within its range. Essentially do a first approximation, none of them. Obviously, it actually can represent some real numbers, but 0% of the possible real numbers in that range. So if we go to a double precision floating point number, that can represent 4 times as many values, which brings us up to still 0% of the real numbers within the range. This is of course useless information because obviously floating point values actually are very useful to us. But for comparison, if I have an integer type in a computer, well, that can represent 0% of the integers also, but within a specific range, like let's say for a 32-bit integer, basically from minus 2 billion to plus 2 billion, within a given range, that integer data type can represent 100% of the integers within the range. Someone on Twitter commented when I made some mention of this that floating point numbers are really just 2 small integers in a trench coat pretending to be a real number. And although that sounds kind of flippant, that actually there's a lot of truth to that. So history of floating point. The earliest computers that had a hardware implementation of floating point arithmetic were actually electromechanical, not electronic. Now, this doesn't go all the way back to Babbage's day, but it goes back to 1938. Konrad Zuse designed and built the Z1 computer, and it used a 22-bit binary floating point format and performed arithmetic on that. It did the common arithmetic functions: add, subtract, multiply, divide. This was built out of relays. That was the start of a series of computers that went beyond this. But the Z4 was the culmination of his electromechanical computers. It was actually commercially sold, although not a huge number of units, and still used binary floating point with a 32-bit format. So the Zuse computers are not really considered. They were pioneering, certainly, but they're not really considered to have had a huge effect on the history of general purpose computing overall. Not at the time. Not very many people knew about them. So people know about ENIAC. They generally don't know about Zuse. So electronic computers, as opposed to the electromechanical, were fast enough that you could implement floating point arithmetic entirely in software. So if your computer only provides you integer arithmetic in hardware, you can just write subroutines to do floating point arithmetic. So that saves you the cost of building the floating point hardware, which back when you were using individual vacuum tubes or transistors, that cost was substantial. And it still yields adequate performance for a fair number of tasks. But if you're doing something compute intensive, if you're calculating well, just about anything that you would do a lot of calculation, then it still is advantageous if you can have floating point hardware, because it's typically on the order of 100 times faster than implementing floating point in software. So the first electronic computer that had floating point, as far as I know, certainly the first mass-produced one, was the IBM 704, which was also known as the defense calculator. It was built with tubes. It was a huge machine. This it was I'm sorry. The 701 was the defense calculator. The 704 was essentially IBM's second big scientific computer. Both with vacuum tubes. The 704 was essentially the kind of computer that Tom Watson was talking about when he said that he thought there might be a world market for perhaps as many as a dozen computers. People have given Watson a lot of flack for that comment, and it's because the comment's taken out of context that Watson wasn't saying there was only a world market for 12 computers of any kind ever for the, he was saying that the market for expensive, gigantic electronic computers was small, and that was absolutely true. By 1969, the IBM 1620, which was a transistorized computer, is an example of a computer for which floating point hardware existed, but it was not standard. It was an option that you had to buy separately, which is more similar to the coprocessors that we're going to talk about. By the 1970s and 80s, many computers offered optional floating point processors, and they still consisted of a lot of electronics, so it was an expensive option. So if you didn't need high performance floating point, then you didn't buy that. By comparison, though, the really big computers like mainframes, floating point was still standard. So getting to calculators, the HP 9100A desktop calculator used radix 10 floating point, and that was essentially hardware, although microcode was involved as well. Now, in real high performance floating point, everything is implemented entirely in hardware. There's no real microcode to speak of, or very, very little. But using a combination made it much more cost effective. They couldn't actually build a computer that size that implemented floating point entirely in hardware at that time. And for a calculator, now the 9100A was programmable, but it was essentially typically manually operated by humans, and so the actual speed that it executed a division or a trig function wasn't all that important. It was a reasonable trade-off to use microcode and not have it be quite as fast, but make it compact and inexpensive. And I say inexpensive, of course, it was still thousands of dollars, which in 1968 started approaching the price of a car. Then 4 years later, 1972, as probably everybody in this group knows, the HP 35 was HP's first handheld calculator. It was also the world's first handheld scientific calculator. Still used radix 10 floating point for reasons discussed earlier. And in this case, the floating point was implemented almost entirely by microcode. So the hardware really did only provide integer operations, but it had some special characteristics to make implementing floating point on it more efficient than if it truly only had integer arithmetic. So fast forward a few more years to 1978, Intel announces the 8086 microprocessor. This is the forerunner of basically all modern x86 personal computers. To this day, if you buy an Intel, Core i7 or something, it still can run software with certain limitations, software that was written for the 8086 back in 1978. Okay, in 1980, Intel announced the 8087 numeric coprocessor, and this was designed for use with the 8086, implemented floating point in binary, and it used a draft standard floating point format. We'll get to the standard later, but the key thing here is that Intel was actually involved in developing that standard, and they were using the draft before the standard had actually been ratified. So there are minor differences between what the 8087 supports and what the final standard did. So year after that, IBM introduced the IBM personal computer. And so most of us now use computers that are compatible with it, trace their lineage back to that. Use the 8088, which was a 8-bit wide bus version of the 8086, so not exactly the 8086, but very, very close. It was, as far as I know, the first computer that had a socket on the motherboard. Well, I shouldn't say first. The first really common computer that had a socket on the motherboard for a numeric coprocessor. There were a few kind of less well-known computers before it that were 8086 based and would accept an 8087, but IBM I think gets credit for popularizing that. Okay, 8 years later, Intel introduced the 486 processor, which was the second 32-bit processor in the line. And although they offered some versions that it was disabled, the 486 was the first mass-produced microprocessor that actually had floating point as standard. You no longer needed a coprocessor. It effectively had the coprocessor built in. So I mentioned the standard. The actual IEEE 754 standard for binary floating point was in 1985. It was ratified. There had been a lot of fighting over the details because different vendors wanted to use their own standard. DEC really wanted to push VAX floating point as the standard, and the IEEE committee that came up with the 754 standard, the proposal, which ultimately was adopted, was interesting in that they had very good rationales for everything they did. And so to the extent that it was different than VAX floating point, it was different for good reasons, not just because we don't want to adopt some vendor's existing standard. Part of the pushback against adopting 754 was it was viewed as essentially being the Intel standard because Intel had participated in the development. But ultimately it was ratified, and now almost all modern computers use that. So single precision has a range of, it's about 7 digits precision and range of about 10 plus or minus 10 to the 38th. Double precision, 15 digits precision, range about 10 to the 1022nd, which if there's any commonplace need for floating point numbers outside the range of plus or minus 10 to the 1000th, I have not ever heard of it. There's also potentially an IEEE extended precision format, which has even more precision, and actually the x86 processors, the floating point supports the extended precision. IEEE didn't specify the exact details of extended precision, but the Intel format is 80 bits. And more recently, the latest standards actually offer a quad precision or 128-bit format. So 1987, because not everybody wanted binary floating point, there was the IEEE 854 standard for radix independent floating point. It wasn't necessarily specifically decimal, although that's the only form that I'm aware of anybody implementing. And there may have been other implementations, but arguably the most famous and popular implementation was the HP71B handheld computer. So this was a handheld computer that primarily ran BASIC, although it had a calculator mode as well. It was the first product to use HP's Saturn processor, which later became more famous for being in the HP 28 and 48 and related models. So it did use the IEEE 854 draft standard. It fully implemented the standard, had 12 significant digits and a range of plus or minus 10 to the 499th. So many other HP calculators have since used code from the 71B, although they tended to drop some of the features that were not needed because the calculators generally didn't need full IEEE 854 compliance. And more recently, in 2008, the 754 standard was revised to include decimal floating point. Depending on what sources you look at, there are claims that 754 includes all of 854. I'm not entirely sure that that's correct, but it does include decimal floating point. So now we can talk about early floating point coprocessors. So the earliest ones in the mid-70s were based on calculator chips. Now there were some hobbyists that actually took real calculator chips. By that time, a calculator, early electronic calculators, including handhelds, had multiple chips. But by the mid-70s, calculators were primarily a single chip, although in some cases they also had a display driver chip. And so there were hobbyists that interfaced those to microprocessors in order to get floating point. Now, at that time, let's say 1975 to 77, hobby microcomputers did not have very much memory, maybe a few kilobytes of RAM. And so if you loaded up your RAM with floating point routines, then that didn't leave you any RAM for your own software. So if you interfaced a calculator chip, then which were inexpensive by then you got floating point without using up your memory. So TI and National Semiconductor said, oh, well, our calculator chips are essentially a very small 4-bit microprocessor that's been programmed to be a calculator. We can modify that firmware to make it easier to interface, instead of to an LED display and a keyboard, to interface to another processor. So that was the birth of floating point coprocessors, at least as chips that someone could buy. Calculator chips are very slow. So arithmetic functions might take 10 milliseconds, and a transcendental function might take as much as a second. Again, not too bad. You're using your calculator and you punch cosine, and if you have to wait a significant fraction of a second, well, I guess now in the 21st century we would be annoyed by that, but in the 70s, it was amazing that you could do it at all. So people didn't complain too much if it took a second to compute a sine or cosine. So as far as I know, the first floating point coprocessor of this nature was in 1976, a Texas Instruments TMS 1018 number cruncher. There's no technical documentation on this chip known to still exist. The internet barely even knows of this chip. There are mentions of it in some TI general microcontroller documentation. Because of the time it was introduced and what TI was doing in calculators and microcontrollers, this is presumed to be a mask-programmed version of a TMS 1000 microcontroller, which was a 4-bit PMOS part. And today, everybody uses CMOS circuitry for everything, but there were a lot of other logic families and semiconductor technologies in the past. And one of the earliest ones for digital integrated circuits was PMOS, which stands for P-channel metal oxide semiconductor. And PMOS was easy to manufacture, but is very, very slow. In 1977, National Semiconductor introduced their floating point coprocessor, which was an MM57109 number-oriented processor. So this was based on their 5799 microcontroller, which had also been used in some calculators. That was it was a single chip microcontroller with a pretty limited amount of ROM and RAM. It was also PMOS like the TI, so very slow. PMOS also runs on different voltages than more modern processes. So mainstream microprocessors at that time, like the 8080 or Z80 or 6502, were NMOS. And NMOS was mostly TTL compatible, and PMOS chips tended to only be partially TTL compatible, if at all. So interfacing was a little bit more complicated. And also because it was, fairly crude early technology, that some of the timing requirements were difficult to meet. So hooking up a 57109 to your microcontroller to get floating point was not entirely a panacea, and it was not necessarily really easy. As I said, very slow, but it may still have been cost effective. As I said earlier, it reduced the amount of memory that you needed on your main processor. That, because memory sizes expanded rapidly and costs went down rapidly, this trade-off was not a good one for very long. But in 1977, it was not bad. The other thing about the 57109, as compared to some of the others, is that electronic hobby magazines ran articles about it, including Radio Electronics and Byte. And so hobbyists built some of their own interfaces to this chip, either based on information in those articles or just designing it from the data sheet. And Southwest Technical Products, which was an early pioneer of 6800-based microcomputers, offered a kit that plugged into their backplane of their microcomputer and had this chip. And they also had some software to help use it. In 1980, National introduced an updated version of it, the 57409, they called a super number cruncher. It was not pin compatible, wasn't a drop-in replacement. It was NMOS, so it was a little bit easier to interface. And that was essentially the last dying gasp of calculator chip-based floating point processors. I'm not aware that this was designed into any products at all. I suppose it must have been, because I was able to buy a few of these chips from a reseller, but they're very uncommon. All these chips are uncommon now, but as far as I know, this one was uncommon even back then. So for comparison, if we look at DEC low-end mini computers. There was the PDP-1103 or LSI-11, and the PDP-11 was a family of mini computers introduced in 1970, and it spanned a broad range from low-end, slow, and relatively inexpensive mini computers to fairly large and expensive high-performance ones. The 1103 was the low end of the range. That was the first one that was based on custom VLSI chips, which were made by Western Digital for DEC. And they offered this KEV11A chip, which was a floating point chip for the 1103. Well, it's not really a coprocessor, it's just a microcode ROM. It added floating point instructions to the instruction set of the main processor. And since it's microcoded, it's faster than software floating point, but it's not as fast as floating point hardware. All of the floating point processors DEC offered previously, which were perhaps better known as floating point accelerators, were multiple printed circuit boards and fairly expensive. So this was DEC's first low-cost floating point hardware, and possibly the first low-cost floating point hardware for any mini computer. So in 1978, AMD introduced what I would consider the first high performance floating point chip, and this was a single precision 32-bit binary floating point unit. It did not use an industry standard floating point format because there wasn't one yet. Although it was only single precision, it included transcendental functions, so that was actually a big selling point. The national chips I mentioned before also did transcendental functions, but of course they were very slow. And the 9511 was much faster, about 50 times faster than those calculator-derived chips. This came about even though it's microcoded. It was designed for the ground up for floating point, so all of its internal data paths are optimized for floating point. And arithmetic functions were usually under 100 microseconds, and basic trig functions were under 2.5 milliseconds. So still slow by 21st century standards, but a big improvement back in 1978. Interfacing was still a little bit tricky. It was NMOS, so the electrical characteristics weren't too bad, but for various reasons, the design of the chip was such that it was moderately difficult to interface to microprocessors. And in fact, AMD published applications information showing what was required to interface to common microprocessors at the time. There were third-party add-on cards for a lot of microcomputers like the Apple II. I'm not aware of any microcomputers that had a socket for 9511 as standard. And so if you added a 9511 card to your Apple II, then you could load into RAM a modified version of AppleSoft BASIC, which was the Microsoft BASIC for the Apple II, that would use the 9511 instead of its software floating point. The drawback of that on an Apple II, though, was that software floating point actually was 40-bit floating point that had 9-digit precision. So when you used the 9511 chip instead, you actually lost precision, even though you gained speed. And Intel second sourced that part as the 8231. An Intel spokesman once famously said that the biggest innovation that AMD ever had was cloning Intel, but this is an example of Intel licensing an AMD design. Of course, more recently, that happened, and in a more important fashion, when Intel adopted the AMD 64-bit extension to x86. So 2 years later, AMD introduced another chip, the 9512. Now, as I mentioned, the IEEE standard was not actually ratified until 1985, but the 9512 chip used the draft IEEE standard as well, because even in 1980, it was obvious that the world was going to go to IEEE floating point. So as far as I know, the chip design internally is quite similar to the 9511, and that meant that the performance might not be optimal for IEEE, and also they added double precision to this chip, which the 9511 didn't have. But as a consequence, they didn't have room in the microcode for the transcendental functions. So this chip only does arithmetic, not transcendentals. It does include integer conversions, which is quite useful. The 9511 chip had those as well. It's still NMOS, but it's slightly easier to interface to the 9511. With the benefit of experience, they saw what some of the difficulties were with the 9511 and improved them. And this one was also second sourced by Intel as the 8232. So we get to 1980, the Intel 8087 mentioned previously. Completely glueless interface to the 8086 or 8088. No added circuitry of any kind was necessary. It basically basically all the signals on the 8087 socket were just wired to the corresponding signals on the 8086 or 8088 socket. So very easy to use with those Intel main processors. On the other hand, compared to the previous chips, this one was difficult to use with any other main processor because it was only intended for use with the 8087. It's purpose-built for IEEE floating point. Used what Intel called HMOS, which was NMOS, but higher density than normal NMOS. Really all NMOS went that way, but this was a case where Intel was in the lead in process technology. It had microcode, and unlike everything previously mentioned, the microcode ROM actually stored 2 bits per memory cell. It was, as far as I know, the first chip to ever do that. Modern NAND flash stores 2 or 3 or even 4 bits per cell, but this was the first chip that did that. It was the fastest floating point chip at the time. An addition typically took about 17 microseconds. This is on a 5 megahertz chip. They actually offered faster ones later. Single precision multiplication, 19 microseconds, double in 27. And then it only had a limited number of trig functions, but it could do a tangent in about 90 microseconds. That was just blazing fast at that time. So, to sum things up, the evolution of floating point hardware and general purpose computers, the 1940s through 1960s, floating point was actually a standard feature of a lot of big computers. 60s through 70s became optional on some computers, but it was expensive still. Mid 70s, we started to see floating point coprocessors based on microcontrollers, really based on calculator chips, which are microcontrollers. Late 70s through 1980s, purpose-designed floating point coprocessors, so higher performance. And then 1990s to present, floating point went back to being a standard feature on microprocessors. So it's really, there's almost no cases today where floating point is optional. Microcontrollers often do not have it, but it's not something that can be that is normally added on with another chip. If you want a microcontroller with floating point, there are some that you can buy. So that's the end of the presentation. I will open things up to questions.
Thanks, Eric. I think everybody should be able to open ask questions. Come off mute if you want to.
This is Gene. I remember in 1984 having a 8088 or 8086, probably 8088 computer doing Lotus 123, one of the early spreadsheets before Excel. And it had a ton of just plain multiplication, division, and so on being done that took forever. I think you had to hit F9 for it to start calculating. And it would just sit there flashing red, wait, whatever. So I convinced the people that owned the business to buy an 8087, pop the thing in, and it was amazing because then it would only flash for 2 or 3 seconds. So I don't know that later on in the 386 world, you could get a 387 chip and pop it in. I don't know that math coprocessors seemed to help as much later. Maybe the standard processor was faster at the time, but I do know in the 8088 world, it was an amazing difference being able to pop in a chip, even for just multiplications and additions and things like that.
Hey, Eric, you didn't mention the 8386. I recall that it used an 8287 coprocessor. Do you remember that, and what the difference was between that and the 8087?
Oh, the 386 could use a 287, but there was a 387, and generally it just continued the trend of making the floating point performance higher. There were significant differences between the 8087 and the 287, mostly in terms of better compliance with the actual ratified IEEE standard. So as Gene said, for spreadsheets that did improve the performance a lot, but he didn't see as much improvement when he had a 386. And part of the reason for that may be that when Excel appeared and ultimately took over the spreadsheet world, Excel, for the same reason that calculators don't use binary floating point, Excel didn't use binary floating point either. Excel implemented decimal floating point in software so that you wouldn't have the rounding problems trying to represent negative powers of 10 and such. So I gather that there have been some versions of Excel that could be configured to actually use the host binary floating point, but normally they do not.
Thank you.
Also around that time, the floating point became standard in what was the DX, and you have to buy the special SX that had no floating point built in.
Right, and it's an interesting point because the die still had the floating point. It was just disabled.
Right.
There was a lot of talk on the internet about, that they used rejects for that, and to the best of my knowledge, that was never done. That they didn't have reject parts and sell them as down spec parts. I mean, that may have happened for some other things, mostly memory, but I think that's rarely, if ever, happened on processors. What happened is testing a microprocessor is an expensive process. There's a like a Genrad tester machine, a machine that costs hundreds of thousands of dollars, and it tests parts one at a time on the assembly line. So Intel or whatever manufacturer would have had more than one of these, but that's any amount of time that the chip has to spend in that tester being tested costs them money because all the chips have to funnel through there. And so if a chip spends 15 seconds in a tester versus 8 seconds in the tester, that literally impacts the bottom line of the chip manufacturer. So if they can sell you a part that the floating point has not been tested and has been disabled, then the test time is lower. And so even though it's the exact same die, the cost is lower. And so I believe that was what was going on with the 486SX. But the interesting part was, unlike the earlier processors, you could add a floating point coprocessor to it, but that coprocessor that Intel sold you, it was called a 487. It was really a 486 with a different pin out. And when you plugged that into your computer that had a 486SX main processor, what it did is it disabled that main processor and it just completely took over. Right. So in that sense, although you could view functionally that, I plugged it in, it's a floating point coprocessor, really you were just replacing the processor.
At the time, Intel shared some information that basically said it was far cheaper for them to make the same die disabled because the QA process only had to make them test the disabled part rather than retest a whole new die. So,
That's right.
They were pretty opaque about the whole thing, though.
Yeah, I mean, semiconductor vendors are generally tight-lipped about anything that involves their processes as it would impact their bottom line. I mean, they were tight-lipped about it, but it was kind of an open secret. Everybody knew or could figure out what was going on, especially their competitors. It was not rocket science. So the competitors all did basically the same thing.
Sounds a bit like the Casio calculator that my mates had at school. I remember one of them spent the extra money for the one that had got the 4 extra labels printed on the shifted functions. And then the other guys found out that the same functions still worked. It's just there were no labels on the keyboard.
Yeah, and today, if you look at the range of Casio scientific calculators, they make multiple models that have identical hardware. They have different labels printed on them, and they have different firmware loaded. So so the manufacturing cost is the same, but you pay more to get the calculator that has more functions. And in some cases, Casio's moved away from this since it was found out. But in some cases, you could open it up. Actually, there was the same firmware in different models. You could open it up and jumper a couple of pins together and turn your lower end calculator into a higher end calculator.
Yeah, I seem to recall my mates did that by taking an indelible pen and just writing labels on the keyboard. Anyway, from YouTube, Martin, oh, I don't know how you say that. Hepel? I'm not sure. What about Vitek, is it? Or coprocessors existed for some PCs, such as the HP Vectra RS20, but were never very popular. Do you know that?
Yeah, in order to keep the talk short, I originally wrote up a outline for what I was going to talk about, and I included a lot of things that I had to cut for brevity. The Vitek chips are one of those. Vitek was an early maker of general purpose floating point chips, and most of their chips met the IEEE standard. But they were dedicated hardware, even more so than the AMD 9511 that I mentioned, or the 8087, and they were optimized for very high performance. So only a few clock cycles to do a floating point add or a floating point multiply, and since they were very general purpose, they weren't as much designed to tie to a specific chip like an 8086. But their original chips, you had to buy a separate chip for an adder and for a multiplier. So later they had combined chips that could add and multiply, and later than that they had some that had additional functions and that actually were intended to interface to the x86. So yeah, I didn't mention them. I don't know all that much about them. There's some information about those on the internet. Actually, when I was at university, we used some of those early Vitek chips. Vitek was actually founded by some ex-Intel employees. They left Intel to go make higher performance floating point because Intel apparently was not very interested in that market at the time. So their big customers early on were companies that were making floating point accelerators and vector processors that were for use with big mini computers like VAXs. And the microcomputer market was kind of a small potatoes for them early on, but increasingly became of interest to them. And so, as I said, they did ultimately introduce some parts for the x86. The interesting thing about it is that they did not, although they made parts that would plug into certain PC motherboards like that Vectra that was mentioned, they provide high performance floating point, but it was not actually compatible with the Intel floating point processors. It did not use the same instructions. So you actually needed special software to take advantage of those chips, whereas if you put an 8087 or 287 or 387 into your PC, then there was a vast amount of PC software that knew how to use it.
Eric, as a big 71B fan, for years I read, the journal and so forth, talking about the role of IEEE 754 and the 71B, and it inferred that HP was a major player in the development of that. Is that correct, or did they just contribute to what Intel was the main thrust on?
I think I'm not really familiar with the history. I suspect that HP was heavily involved in the development of the 854 radix independent floating point. I don't know how much they participated in 754, although they probably were involved in that as well. If you look in the actual standards, which I don't happen to have at hand at the moment, but they generally list the representatives of various companies that were involved in developing the standards. So if you look at those standards, that'll give you some idea as to the involvement.
Thanks.
So Eric, are you aware of what companies like NVIDIA does on their graphics processors? Are they, how do they implement numerical processing?
Well, they have they have a lot of dedicated hardware that does highly efficient implementations of IEEE floating point, and these chips for a long time only did single precision floating point. And when they started offering double precision, that usually had much lower performance. But the interesting trend there is although all the new chips do support double precision, and for some That's not used a whole lot typically for graphics. It's usually used for other types of computing, going to double precision. But the new thing, the new trend in them is to offer half precision. And the rationale there is that they can do half precision. For instance, in a vector unit, you can do twice as many operations per cycle. And no, you don't get the precision, but what you get is is just increased throughput. And it turns out that for machine learning, for artificial neural networks, that half precision is good enough. And this has started appearing now in general purpose processors as well. The latest Intel AVX sort of stuff includes half precision now.
Thanks a lot. Appreciate it.
Rick, there's Apple and various other people make a big deal about these AI chips that they're putting in. Does that include that type of half precision floating point type function? Do you know? Is that the sort of thing? I've not looked into what they contain, or if did they even tell you what they contain? I'm not sure.
I haven't either. I suspect that they probably do have the half precision, or there are actually some alternative floating point formats that are not IEEE compatible that kind of have variable precision depending on the exponent, and there are some advantages to that, and they might be using that. So this really came to the forefront. There were other things in the market, but this really came to the forefront when Apple put AI coprocessor capabilities into their new M1 chip that's used in the latest MacBook and Mac Mini, and I think that trend it's hard to say whether that'll continue forward a lot or whether it's a flash in the pan sort of thing. The processor vendors, try to in general purpose processors add instructions to handle common computational loads, which going forward is going to include this type of processing. So as far as I understand it, in the M1, this AI coprocessor really is kind of a bag on the side sort of thing, and that's not intended as a dig at it, but what it indicates is that they didn't yet think that it was time to just make that a core CPU function. And I think over time, just as floating point was not really originally a core CPU function in microprocessors, but it has become one. I think the same thing is likely to happen with any AI-oriented sort of up processing. I've taken a few classes in machine learning topics, and I'm far from being an expert at this. So it may turn out that I'm totally wrong, and maybe 30 years from now, your microprocessor chip will actually the actual processor will be a little tiny thing in the corner, and the whole rest of the chip will be special AI processing functions. I have no idea, but the trend historically has really been to add new types of computational functionality to the core capabilities.
Thanks. Eddie, do you want to ask?
I was wondering if you knew that if all the modern all the calculators used today, do they use chips that are on the IEEE 754 standard?
Calculators mostly do not, because they still want to do decimal floating point. And although the 2008 edition of the IEEE standard includes decimal floating point, there's very little hardware in the world that supports it. IBM mainframe computers are really one of the only ones. I've been optimistic that decimal floating point hardware will appear more widely available, but to date that has not happened. And so I think very few, if any, commercial calculators use floating point hardware.
I think the 71B is the only commercial calculator that ever implemented 754, or at least promoted that.
854. Yeah, I think you're right. If there's been any other implementation of 854 that is fully standard compliant, I have never heard of it. You know, when HP and the other companies that worked on 854 developed it, I'm sure they all expected that you know that would see more widespread adoption than it has.
Another way to look at it is how many calculators have you seen answer not a number, right? Only the 71 will do that.
Yeah, not very many. I always think it's amusing when you see errors in websites where they have done some computation and they haven't done proper error handling, and so they'll you know tell you that some value, maybe the price of something, or you know they'll you know there'll be some place where you expect a number and it'll say nan, and you know that's a result of sloppy programming, just not anticipating that an error could occur. The worst case of that is when you see you know some like physical sign somewhere that is trying to present information to you, and it'll say nan, and you know multiple times I've seen this. You can find photos of this you know on the internet. You know it's similar to, maybe not quite as bad as when you see a physical sign somewhere that has a Windows blue screen.
Or more disturbingly, I've seen that on a ATM. You know, bank
Yeah.
money. Yeah.
Yeah, where you really don't want to see it is on the
No.
glass cockpit avionics. And as far as I know, there aren't any aircraft that the avionics runs Windows. But you know, if that occurs, your blue screen of death might be literal.
Yeah, the word crash is not what you want to hear in those circumstances, is it?
I do have a cartoon somewhere sat in a folder which says, which is a man sat on an aeroplane with the message on his computer saying, "Found new device Boeing 777. Would you like to pair with this device?"
Yeah,
Anyway.
Boeing got a waiver on the 787, and I was very disturbed by it. The traditional rules for aircraft design, no non-essential systems can be electrically connected to actual flight support systems. And so historically, that meant that if you were on a 737 and watching the in-flight movie, or using an entertainment system, or using back when they had airphones, none of that was in any way electrically connected to the systems that controlled the plane. And Boeing actually got a waiver for that on the 787, and I think that was a huge mistake. And you know, I'm not aware that it's caused any problems since. The justification for it was so that the you know, and this has been done on other aircraft, but the justification was so that the in-flight entertainment could show the you know the route and speed and you know position and so forth. And to the extent that that's a desirable feature, you know, and I'm not saying it's not, but to the extent that it's a desirable feature, that shouldn't have been implemented by combining the buses. There should have been a gateway at one point that was a unidirectional gateway that was physically incapable of passing any information the opposite direction. And they did not do that. So, you know, who am I to say how Boeing should design planes? They're the experts and I'm not, but it just didn't seem right to me. And the 737 Max debacles, of which there have been multiple, I think show that Boeing management is ignoring engineers and making management decisions that, instead of saying we're going to do the engineering to make the aircraft safe, they're saying the aircraft is safe, so we're going to cut the engineering to save money, and which is the opposite of how things should be run.
Indeed. Right. Thanks, Eric. That was very interesting talk.